A supernova is the largest eruption ever observed by humans. Each detonation is the incredibly brilliant and incredibly powerful outburst of a star. One variety of supernova is caused by a dying massive star's last effort. This occurs when a star with at least 5 times the mass of the Sun explodes with a tremendous explosion. Massive stars consume vast quantities of nuclear fuel in their centers, or cores. This generates enormous amounts of energy, causing the center to become extremely heated. Pressure is produced by heat, and the pressure produced by a star's nuclear combustion prevents the star from collapsing. A star maintains equilibrium between 2 opposing forces. Gravity attempts to compress the star into the smallest, most compact spheroid possible. However, the burning of nuclear fuel in the star's interior creates a significant outward pressure. This outward thrust resists gravity's inward compression. An enormous star cools down when it runs out of propellant. This results in a decrease in pressure. Gravity triumphs and the star collapses abruptly. Imagine something with a mass 1 million times that of the Earth disintegrating in 15 seconds. The collapse occurs so rapidly that it generates immense shock waves that cause the star's outer region to erupt. Typically, a dense nucleus and an expanding cloud of hot gas termed a nebula are left behind. A supernova of a star greater than approximately 10 times the size of our Sun may leave behind black holes, the densest objects in the universe. Think about being an astronomer at the start of the 17th century. As the telescope has not yet been developed, you must use your limited vision to explore the universe. Then, one day, you see a truly spectacular scene. In the next several weeks, a new star will shine brighter than Venus. Very high levels of brightness make it visible throughout the daytime. As the months pass, it fades somewhat but persistently in the sky. Skywatchers across Europe, the Middle East, and Asia all witness the same thing that the German astronomer Johannes Kepler did in 1604. Now we know it was a supernova explosion, a massive explosion, that occurs when certain stars approach the end of their lifetimes, and not a new star. The latest supernova to occur within the Milky Way was in 1604. Maybe more nearby supernovas have occurred since then, but they have been veiled by interstellar gas and dust, and hence have not been noticed. The Crab Nebula is an example of a remnant of a supernova that occurred thousands of years ago. Its light reached Earth around 1054. The supernova discovered in the Large Magellanic Cloud in 1987 was the closest thing to Kepler's supernova in recent years. In addition, several supernovae in other galaxies have been documented. These may be seen with the naked eye, but only with a telescope. Skywatchers in Kepler's day would have missed them totally. Hence, it has been 418 years since we last witnessed a star explosion in our galaxy. Is a close, brilliant supernova therefore long overdue? Scientists predict that between 1 and 3 stars should burst in our galaxy per century. If the next supernova occurs, modern astronomers will be better prepared for it than Kepler was, or even scientists from only a few decades ago. Astronomers now have access to telescopes that can record visible light. When used together, these equipment will simulate the experience of flying near to a supernova and observing it with our own eyes. In addition, we have telescopes that are sensitive to infrared light, or light with wavelengths that are beyond the red end of the visible spectrum. Infrared light, with its longer wavelengths, may penetrate gas and dust more easily than visible light, allowing us to see objects that might otherwise be hidden from view with conventional telescopes. Examples of instruments that predominantly record in infrared include the James Webb Space Telescope. The electromagnetic spectrum includes both visible and infrared light. However, neutrinos, which are subatomic particles, are also emitted by supernovas, and modern detectors can capture them. Also, astronomers now have detectors that can record gravitational waves, which are tiny vibrations in the fabric of space-time thought to be released by exploding stars. In the scientific literature, two kinds of supernovae have been identified. When a white dwarf star undergoes a Type 1 supernova, it sucks material off of a partner star until a runaway nuclear reaction occurs, causing the white dwarf to be blown apart and send debris hurtling into space. As a star runs out of nuclear fuel, it collapses under its own gravity and bounces, setting off an explosion known as a Type 2 supernova. There have been instances of both types of supernova being brighter than their host galaxy combined. The tremendous amount of neutrinos that are released alongside the light makes Type 2 supernovae very fascinating. Neutrino emission can actually begin before the explosion happens. Even though the field of neutrino research was in its infancy when the explosion of 1987 occurred, 3 detectors were able to record a total of 24 neutrinos. One may expect hundreds, if not thousands, of neutrinos to be recorded by the global network of detectors should a supernova burst within our galaxy at this time. Very provocative signals might be produced in the event that a falling star forms a black hole, therefore preventing the explosion from producing any further stellar debris. In those conditions, the neutrino stream would abruptly cease. It would be awesome if you could see the black hole's sharp boundary, which indicates its formation. The missing star might then be identified by comparing it to other stars in astronomical databases. A lost star might be the site of a freshly generated black hole. Successful discovery of gravitational waves from a galactic explosion would round off the hat trick. Gravitational waves, which Einstein said would exist when a huge body was accelerated, are distortions in space-time that are produced as the mass of the body accelerates. Such signals were identified for the first time in 2015. Black hole and neutron star mergers are responsible for the gravitational waves seen so far. Yet, when a supernova does occur in our galaxy, it should also be seen. Computer models of supernova explosions have been used by astronomers for decades, but many features remain unknown. Knowledge gained from studying gravitational wave data may shed light on the method. What danger may a closed supernova pose to life on Earth? In principle, yes, but the explosion would have to be quite close, since there are currently no nearby stars in danger of exploding. To be sure, a close supernova's radiation outburst would be disastrous, so this is excellent news. The explosion would release harmful UV, X, and gamma radiation into space over a period of weeks, damaging Earth's protecting ozone layer, even if they didn't reach the ground. Without the ozone layer, the sun's lethal UV radiation would flood the planet, killing everything from phytoplankton in the oceans to humans. It's possible that something like this occurred sometime in Earth's past, around 360 million years ago, near the close of the Devonian epoch. A massive extinction may have been caused by a supernova. On the other hand, supernovae are not just destructive forces. They may also give rise to new life. Astronomers and physicists point out that the nuclear processes that take place deep within exploding stars and spread throughout space as a result of the blast waves they create are the source of many of the heavy elements on which humans depend. This means that a supernova would be the new gold standard for astronomers. Thanks for watching. Hope you enjoy it.